In this paper, we examine potential applications of neural radiance fields, or NeRF, in the field of landscape architecture. NeRF is a state-of-the-art method for novel view synthesis and volumetric scene reconstruction based on real-world training data. We generate NeRF models by the application of Instant NGP, an open-source software framework developed by researchers from NVIDIA. We discuss experiments based on the post-disaster landscape of the Ahr River Valley in Germany, affected by a 100-year flood in 2021. Articles on computer science allowed us to develop a basic understanding of what can be generated with a NeRF. The potential of such technology for landscape architecture is gigantic. A NeRF model represents three-dimensional scenes as a radiance field approximated by a neural network. The radiance field describes color and volume density for every point and for every viewing direction in the scene. The original approach by Mildenhall and team represents a scene using a fully connected deep network whose input is a single continuous 5D coordinate, x, y, z makes 3 plus 2 viewing directions makes 5, and whose output is the volume density and view-dependent emitted radiance at that spatial location. NeRF models use two-dimensional RGB images and their camera position to create synthetic three-dimensional scenes. For data acquisition, we used field-ready devices like a DJI mini drone and smartphones. To capture our field scenes from different perspectives, we mostly produced camera orbits and loops, as we can see here. We try to capture the horizon as well, because NeRF models feature great landscape suitability. NeRF have the attribute of photos or videos to show the full context of a scene. After the collection of footage in the field, we use Instant NGP, standing for Instant Neural Graphics Primitives. It renders the raw material into new images or animations of widely photorealistic quality. Emerging from the field of computer vision, not from surveying or measuring, the prime focus of a NeRF is to produce visual representations of a scene, surface, or object. The graphic shows the technical spatial extent of a NeRF model. The circle indicates the camera position of the drone. One may comprehend why the context and background is so apparent in a NeRF model. From an aesthetic point of view, in landscape modeling before NeRF, there was always a significant difference between the navigable three-dimensional model and the modeled real scene. NeRF technology yet translates the ability of photography and film to capture the full context of a scene, inclusive the landscape background, into a complex three-dimensional model with an identifiable environmental context. That is something genuinely new. A NeRF generates a detailed reconstruction of variables including light intensity and transparency. This results in unprecedented 3D realism. Customary techniques like point clouds result in models detached from their physical context, the surrounding landscape. Where the LiDAR scanner ray ends, a black hole opens as model background. Christophe Giraud describes the related digital aesthetics as cloudism. In regard of the possibilities of NeRF, we suggest to counteract the newfangled term cloudism again with a classic term, realism. A landscape model is still understood best by layperson and expert when it corresponds to the common appearance of the real landscape. Instant NGP trains a NeRF in seconds using multi-resolution hash encoding. The model is constrained by a unit cube bounding box with the highest resolution at the center. We did not exploit the full potential of NERV technology, but we were able to identify some of its specific upsides. A NERV differs from all the traditional 3D scene formats commonly used in landscape architecture. With NERV, a simultaneous movement through time and space is literally possible. We call it multi-temporal NERV. Such models allow to visualize ongoing processes and all kinds of patterns of change, not only useful for disaster areas. As landscape architects, we consider NERV most effective for all purposes of representing before-after conditions of a site. The example combines 2 drone flights in 2019 and 2022 over the village of Rech. Instant NGP's graphical user interface provides a set of visual debugging tools that can be used to uncover the internal structure of input and output neurons. For our case study, dealing with flood scenarios, we used the partial activation of neurons as a rising green light field to simulate the rising waters. A simple yet very powerful tool for flood simulation with full visibility of all model elements. It's an important task to think of a landscape model not as a static set of coordinates, like point clouds, raster, or vector data, but as a set of parameters that are constantly changing. The fact that NERV crosses the border between modeling and simulation suits the instability and openness of the landscape subject. Anyway, never neglect navigation. You may end up in a tree and crash. Thank you for your attention.